Sıradaki konuşmacımız ABB'den Domagoj Talapko. Kendisini alkışlarınızla sahneye davet ediyorum.
Hello all, hoş geldin. Thank you very much for joining. My name is Domagoj Talapko. I'm a Global Business Development Manager from ABB for the power protection. I will give my best to tell you a little bit more today about some of the challenges that we see in the data center space today and how we can actually tackle them. We see that perhaps thinking outside of the box is a very important part of this equation and this entire endeavor. So I would definitely like to ask you to try to think a little bit differently throughout this presentation. We are all very well aware of the challenges that we have today in the data center space. One of those is definitely that the power densities are increasing, and also the connectivity for the data centers is becoming a significant issue and challenge today. We know that 15, 20 years ago we were talking about data centers of 100 kilowatts perhaps. Today we are easily talking about a scale which is at least 1,000 times more. We are talking about 300 megawatts, 500. There are even gigawatt projects out there. And we know that this is creating a significant challenge in how we can develop these infrastructures and also how we can create the points of connection to the grid. Furthermore, we also know what is happening in the AI world very well. We don't need to see it only through the eyes of the data centers. We can also view it from the eyes of the semiconductor industry as well. In semiconductor industry, we see a very strong tension and very strong necessity to create much more chips. And we know that the power densities associated to those systems are also dramatically increasing. We come now to the third problem, actually potential solution to the problem. We know that there is less and less power available in the grid. So how do we tackle it? Normally, when we think about power grids, the potential solution in the power grids is to create relatively fast, responsive type of a system that can generate power. So normally, this is done by the power plants. So we have fundamental ones, but we also have the peak ones. And for example, very often the most trivial way of solving these problems and challenges is associated to the turbine systems. They can be either steam powered, like in the nuclear reactors, or gas powered, for example. Now today, in a data center space, we don't really use that. And there is a reason for it. Today, we are predominantly using the diesel-powered generators because of their responsiveness, because of their ramp-up time. These types of systems require a relatively long time to ramp up and to be online. Also, they are relatively fragile. They cannot adapt very easily to the volatility imposed by the load. So this is a challenge. This is a potential solution for the lack of power, but there is also something missing. One of the potential solutions of incorporating this type of a system can be seen through the means of the state-of-the-art power protection in the medium voltage realm. What we propose is to think about power protection from the MV side, and by doing so, creating a large wall that would protect the entire facility, rather than going with small chunks in a distributed manner in the domain of the low voltage. The way how we can do this is through the architecture, novel architecture, which we refer to as ZISC. Z stands for impedance, isolated static converter. So this is somewhat similar to the rotary systems used in the medium voltage realm, but this is the first time static type of a system that encapsulates all of the best attributes of the both worlds. Ability to work at the medium voltage, high efficiency, reducing the cabling and everything else, reducing the infrastructure, but also at the same time having a very high efficiency and robustness that comes from the static world. So on the inputs, we can definitely have different varieties of choices, different types of sources. We can easily parallel 2.5 megawatt chunks of the UPSs and create 25 megawatt clusters. From 25 megawatt clusters, we can easily create 300, 500, and so on megawatt types of systems and deploy them very easily. This is a short comparison of the traditional low voltage and also compared to the medium voltage. So, for example, here you can see traditional architectures of 25 megawatts. And here, this is the low voltage variant compared to the MV variant. In the LV variant, we have to go down all the way through the medium voltage, which we take pretty much as a relatively simple way of connecting to the grid. But then the complications arise in the low voltage part. And that is where we do our distribution systems, that is where we do all of the automation, that is where we do all of the cabling and everything else. And that is fine. When we have the data center of 5 megawatts, 10 megawatts, perhaps this is still relatively easy to do. Keep in mind, all of the paradigms we were discussing are 20, 30 years old. And back then, the data center sizes were very small. Once when we go into high sizes, then it makes sense to think about stepping out a little bit more, changing the voltage level, and then create the clusters of the medium voltage systems to protect the entire facility. It is normal. When you think about it, when you grow, it is much easier to go into medium voltage because of the efficiency, easiness to install, and all of the other possible attributes. This is the way how we build it. This is the way how we do the approach to the system. Obviously, resilience is a very important attribute to all of the data centers and all of the critical infrastructure. What we can do here is we can create the clusters of, here we have 10 megawatts, for example. So this is a 30 megawatt data center because we have 4 clusters and one of them is redundant. So in case of any emergency or any maintenance was to be carried out, we can easily take entire system offline. And then the system is shared redundant here through these 4 lines. This is just a principle to indicate. So this gives simplicity and ease of maintenance. Now, because the medium voltage UPS is the heart of this entire system, the question is how it really works, right? Can we use the old paradigms to accommodate for this? And the answer is no. We have to use something a little bit different. Because we are at a different level, we also have to use different approach to how we solve this. In this gray area, this is the indication of the medium voltage UPS, consisting out of line reactor, or the choke, step-up, step-down transformer, and power converters. Coupled with this is also the energy storage, in our case based on the lithium-ion systems, to be robust. And what is novel is that this UPS has the automation and functionality together with the switchgear. We always knew low voltage UPSs as systems that work in harmony with the batteries. That's it. In this case, UPS works in harmony with the batteries, but also with the switchgears. This is a triplet that is being reinforced by state-of-the-art automation. How it works. In a normal mode of operation, power flow is achieved directly from grid to the chip, passing through the reactor and through the monitoring points which we have on the input and on the output. As long as there is a perfect sine wave, we don't really do much. But in case if we have undervoltage, like here indicated, indication is known, and the converters inject reactive power directly into the main line and do the direct compensation. So by doing this, this is happening in milliseconds. And we are, by doing so, mimicking an inertia system. Same like the rotary world. But instead, using a real inertia, we are creating a synthetic inertia. We are using a static power electronics at a very high efficiency. I also told you about the switch gears and the importance of the coordination with the switch gears and automation. So here is how it works. And I also mentioned to you about the monitoring points. We observe all of the anomalies happening on the input side of the things. And all of those can be depicted in terms of a nominal voltage and in terms of a duration, here indicated in logarithmic scale. As long as any event, dip, sag, swell, or anything else falls within these red curves, system continues to run on the grid without any issue. However, if you would have an unfavorable event, such as short circuit, for example, in that case, it means voltage is collapsing down to the zero, and we have crossed this threshold, this red line. What we do, we immediately open up the input circuit breaker. And by doing so, we decouple ourselves from the grid. Load is protected. So it is not only the functionality of the UPS, but the automation of the UPS working in harmony with the switchgear and with the batteries. This is the principle of the medium voltage. Of course, in this case, UPS memorizes exact tempo, pace, phase shift, and all of the other parameters needed to continue the perfect sine wave back to the load. Once when the grid is okay, we have the time to trust, then we reclose this circuit breaker and continue to work on the grid as it should be. Now, I told you about the input phenomena. Now this is on the output. This is the other side. This is how we protect the load. This is the performance of the UPS. We are all acquainted with IC 6240-3, and the class 1 is the most stringent class of those all. Here, we have the indication in the dark gray area about the typical performance of the medium voltage UPS. So the idea is to have state-of-the-art dynamic responses. You will see a bit later why this is important. Also, if we want to clear the faults, we need to have a huge amount of the short circuit capabilities, and we can deliver up to 560% of the nominal current for the period of up to 2 seconds. This is important because we don't need to trip all of the circuit breakers so quickly. We can hold, and we never drop the load. Efficiency curve is fairly high. From 50 to 100% loading, we are talking about even above 98% efficiency, peaking at around 98.5. From 25 to 50% loading, we have a small slope, and its average is at around 97% efficiency. All right, talking about the AI. AI is obviously a very, very big topic. It is a challenge for all of the manufacturers today, for all of the OEMs, for all of the UPS technologies, and we know that the signals can have many different shapes and forms. We are acquainted with a few different manufacturers. We know about H100, Blackwell, and many others, variants of the chips available today. All of them have different volatilities, but the common denominator is that all of those are very, very volatile. Now, this is what it depicts. However, few very important attributes here are the play and coordination between the line reactor and the energy storage. The line reactor can be seen in a way as a shock absorber. So whatever happens in terms of volatility, it creates a very stable frame. Now, this is maybe to illustrate also another variant of how we approach it. You see, when you work with the low voltage UPSs, you have no choice but to tackle the high density directly, individual racks. Why is that? We know that today we are talking about 130 kilowatts per rack. We already know that there are programs in place for 300, and we also are aware of some other programs that can go up to 1 megawatt. That means that with a single individual low voltage UPS, you would need to protect individual load. Here you have a very crude simulation or indication of different racks, different systems. Now keep in mind, this is not a real load, this is just a simulation, intentionally, because we cannot show the proprietary data, but it is based on that. Here, we are talking about different racks, different systems. When you take a look at the behavior of individual racks, you will see it looks horrible, right? We have spikes, we have dips, we have everything happening right now. However, if we take all of those 16, and if we connect them to the same busbar systems, and we can do this because we have big systems, then they average out. It doesn't look so horrible anymore. Actually, it is represented on this first line here. If we take even more load, then they average out even more, and if we take even more load, then they average out even more. What does this mean? More is better. More loads connected to the same point actually allows us to avoid the direct issues of the volatility of the AI loads. So just by a simplicity behind, we actually have a significantly good solution here. It is very easy to create the microgrid systems, as we mentioned. We have a lack of power on one side, we have the AI systems on the other. Very volatile, and we have a lack of power. So we can create easily the microgrid systems based on this paradigm of the MV, use the energy storage systems as well, and basically use this type of medium voltage protection as a clutch in between fragile on-site power generation and volatile AI loads. In terms of grid support services, this is a very big topic in general in Europe, and I know for a fact it will come also to Turkey in one shape or another. As the data centers are becoming larger and larger, it is important to help the grid as well. When you are small, then you only take from the grid. But when you become big, then it is also very important to make sure that this grid is also safe, that you don't affect it. And this set of services allows us this. One very important attribute is that we can work with the batteries and with whatever is on the grid, either grid or the generator, simultaneously. And this allows us to manage the long ramp-up times that can last for a couple of minutes. In terms of capital investments, there are obvious and very strong propositions for the reduction in cabling, because we are on the MV. It means also reduction in the man hours needed for the installation of those. Furthermore, in terms of operating costs, it is also a state-of-the-art solution because at the medium voltage efficiency is higher than on the low voltage. Maintenance has its culture as well, and the system is meant to be pretty much maintenance-free. So from all of this, we are coming to a solution which is outside of the box, and I hope it will be accepted by yourselves as well here in Turkey. In general, we have created a very good installed base, and we have made multi-hundred megawatts total different sites in Canada, United Kingdom, Belgium, Australia, United States, and the last project that we are tackling is a 400 megawatt project in the United States. So if you would have any questions or interest in this, please feel free to reach out to us at our stand. And I thank you very much for your attention. Thank you.